I'd like to thank the organizers for the opportunity to speak, and in particular, I'd like to thank the local organizers for doing such a wonderful job in organizing such a big conference. So we'll be dealing with large isometry groups of non-positively curved spaces. I will only consider manifolds, so all throughout my talk, M tilde will denote Hadamard manifold. So will be complete and simply connected of non-positive sectional curvature, and then of course the classical Hadamard-Cartan theorem applies, and we know that M tilde is diffeomorphic to Rn, that any two pairs of points can be uniquely connected by a geodesic, and all such geometric tools are at hand. I will need, at least at one point, the geodesic flow. So the unit tangent bundle of our manifold will be denoted by Sm tilde. So that's defined for all of R, since M tilde is assumed to be complete. And I'll always assume that's the main, coming to the title of my talk, will always assume that the isometry group of M tilde is large in the following sense. So it should be co-compact. That is, there exists a compact subset of M tilde such that if I move it around with all isometries I have, M tilde is completely covered. And I will try to obtain some structural results about which groups can occur. And it's probably a good idea to start with the most prominent examples first. So I will, these are, of course, uniform lattices. So not necessarily in a symmetric space, but I will also talk of uniform lattices as long as gamma is properly discontinuous group. Acting freely, and uniform refers to the fact that the action is co-compact. So in this case, I will have a quotient manifold which is compact, and it's interesting to note that gamma encodes lots of geometric informations about M and M tilde. Let me just give some examples. Of course, gamma encodes all information about the topology of M, since M tilde is contractible. For example, the group cohomology and the cohomology of M coincide. For example, gamma encodes complete information about the number of factors and the dimensions of the de Rham decomposition. These are results of Patrick Eberlein. For example, gamma encodes if M tilde contains a flat subspace which was proved by Andersen and Schröder first, And this happens for example, this can be easily described. It happened exactly if and only if gamma is not a Gromov hyperbolic group. Or gamma encodes if M tilde is a symmetric space of non-compact type. Let me just abbreviate this. Symmetric space of non-compact type. So in the reducible case, this was proved by Eberlein for irreducible such uniform lattices. The general case would be Gromov's rigidity theorem, and then later on Eberlein and Ballmann gave a nice algebraic characterization of those gamma which occur. So all this should be just examples of the fact that a large isometry group catches much of the geometry of a space, so it's worthwhile to investigate such groups also in their own right. And the main aim will be to investigate groups, possibly not full isometry groups, but subgroups which are still large enough to act co-compactly on such a Hadamard manifold. And I already mentioned not necessarily the full isometry group. As soon as you have a group G, there may always be extra symmetries which are not so easy to be seen, or it might even be possible to perturb the metric in such a way that the isometric group becomes smaller. So we will allow to pass to smaller subgroups once in a while, to proper subgroups, as long as these will still be co-compact. And with the aim to obtain particularly nice subgroups, so with a nice algebraic structure. Nice algebraic structure should be our aim, and I will try to explain these structures. So let me come to those examples which have been investigated most for many years. There are essentially two disjoint classes of isometry groups which have been investigated. The first one contains uniform lattices. The second one would be isometry groups of homogeneous spaces of non-positive curvature. And as I will explain in a second, these are essentially disjoint. And it's, I guess, an interesting question to ask if those are really all examples that there are of co-compact isometry groups. So just check. So the main examples are firstly a class which contains a class of uniform lattices. It's contained in the class of groups isometry groups which satisfy the duality condition. So that's an essentially dynamical condition I'll explain in a second. So this condition has been dealt with a lot. And then secondly, of course, there are transitive. There may also, once certain M tilde you may have a transitive and therefore also co-compact group, transitive isometry groups. And in this case, of course, M tilde will be a homogeneous space of non-positive curvature. So these two classes are essentially disjoint. In fact, the isometry group of such a homogeneous space will satisfy the duality condition if and only if it's a symmetric space. So only for symmetric spaces will you have an intersection of both classes. Both have been investigated, and it's a natural question to ask, are there further structures of possible groups which co-compact isometry groups which may occur? And the answer will be, well, essentially no. Everything there is will turn out to be some mixture of both types. So they will in some way, by some extension or semi-direct product method, be the building blocks for all groups which can occur. So let me start with type 1. So the duality condition. Which is defined as follows. So first of all, I look at a single vector in the unit tangent bundle. And those vectors are called non-wandering modulo our group G. So let me start with G being some subgroup of the isometry group, and a vector will be called non-wandering modulo this subgroup if we can do the following. We take some nearby vectors Vn, apply the geodesic flow, and then the derivative of some isometries, and we end up as close as we wish to V. So for that purpose, we would need to take a sequence of tangent vectors convergent to V, some times Tn tending towards infinity, and suitable phi n's in the isometry group, so in our group G. And if this property is satisfied by every vector, then G is said to satisfy the duality condition. So, for example, this will be the case if G is discrete, so properly discontinuous and co-compact and free, not necessarily free even. G is a discrete subgroup. In this case, you would just take, you would look at the action of the group on the unit tangent bundle and choose a fundamental domain. And then that's a very classical result of Poincaré. How would we find for a vector v, a proof for a vector v that such quantities, such times tn's and such isometries exist? So we would want to choose the Vn from an arbitrarily small neighborhood, say capital V of V. So this is a subset of the unit tangent bundle, so we can apply the geodesic flow to it, and we'll soon run out of our fundamental domain, but we can always pull back by our isometries and maybe get here the set U intersect G times GTV if we've applied the time t geodesic flow to our set V. And now the simple fact which lies behind all this is that this will have the same volume. U will have finite volume, so eventually these sets for different t's will keep intersecting each other since there's just not enough space to avoid each other. That's a classical result of Poincaré, and therefore the vector v, each vector v will be non-wandering, and such a group G will satisfy the duality condition. And there's a very nice called dual if there's some set of isometries which maps a base point. Phi n maps a base point close to one point at infinity, one endpoint of the geodesic, phi n to the -1 to the other point. So these pair points are called dual, and that's probably why this notation was chosen. So now there's a theorem from the 80s by Pat Eberlein. If the isometry group satisfies the duality condition, well, dt condition, then without any assumption on co-compactness or whatever, M tilde will be a Riemannian product of three factors, any of which may be absent. The first would be the Euclidean de Rham factor. M1 tilde would be symmetric space of non-compact type, since we're in non-positive curvature and have already split off the Euclidean factor. The isometry group of M2 tilde is essentially discrete. Will be necessarily be discrete. So in particular, if M tilde happens to be irreducible, this will tell us that you have just one factor which cannot be Euclidean, and then either the space M tilde will be a symmetric space, or the isometry group will already be discrete. So here you are somewhere in the middle between transitivity, which occurs for these first two factors, and anything else, all of the rest will only admit a discrete isometry group. So that's maybe all but for that reason I will call isometry groups which co-compact isometry groups which satisfy the duality condition essentially discrete, since in this case we might just as well pick a discrete subgroup or a lattice in M naught tilde and a uniform lattice in M gamma tilde, and the product of these will be a discrete subgroup acting on M tilde. So such group, that's why I will talk about essentially discrete groups. G, or all the isometry group, acts transitively. That is on a homogeneous space of non-positive sectional curvature. So these spaces were investigated in the 70s. The first structural results were proved by Ernst Heinze about negatively curved homogeneous spaces. And then the general case was treated by Azoncourt and Wilson. And I would like to also point out that later on, much of what they did could be simplified by Thomas Wolter. So how do such groups, how do such spaces look like? Let me start with the example all of you know. So a special case would be, of course, a symmetric space of non-compact type. He proved that at the same time and independently that those spaces always admit a simply transitive solvable group. And he knew some of the structure those needed to have. Right, but I should add, so DV Alexeyevsky definitely also contributed. So let me start with a case M tilde symmetric space of non-compact type. So the isometry group or connected component of the isometry group, let me just, to cut things short, take this as our G, would be semi-simple. And let me just assume that it's a linear group. So it's a non-compact semi-simple linear group. And we have the so-called Iwasawa decomposition. Element-wise, the elements of G may be written as elements from three groups: maximal compact subgroup, an abelian subgroup, and a group which is named N for two reasons. On the one hand, it's nilpotent, and on the second hand, it's normalized by A. Which tells us that the set of pairs A times N is again a group. And now we know from Cartan's fixed point theorem that a maximal compact subgroup fixes some point P naught, is a stabilizer of P naught in a homogeneous space. Then of course M tilde can be identified with a coset space G mod K, and due to this product decomposition, just as well with all products of elements from A and N. But since A normalizes N, this is a group, in fact a solvable Lie group, and we can identify M tilde up to isometry with a solvable Lie group endowed with a left invariant Riemannian metric. And that's just what the start, essentially the start, what definitely Alexeyevsky knew, and what was a starting point for all these investigations. So the general case of non-positively curved homogeneous spaces would be just the same observation. Any such homogeneous space can be modeled on a solvable Lie group equipped with a left invariant metric. And it's maybe helpful to get a feeling for that to describe some geometric features. So for example, so let's see, for example, one parameter subgroups in A are geodesics. And the union of all these geodesics, so the group A considered as a submanifold of M tilde, turns out to be a flat subspace of maximal dimension. But then there are specific one-parameter subgroups which have additional nice properties. So there exists one, and actually many, of such one-parameter subgroups with the following property. Every killing field coming from the nilpotent group N, and every N killing field decays exponentially along this geodesic phi tilde. And we already know how A killing fields behave. Now N killing fields get smaller and smaller, and from this one can conclude that the group A times N actually fixes the corresponding point at infinity, so the point of all equivalence classes of asymptotic rays which are asymptotic to phi tilde. So this group fixes phi tilde of infinity. And actually, so we have our A identity element and one of these one-parameter subgroups phi tilde, and actually there are more, all which satisfy these properties will build, just as for symmetric spaces, a Weil chamber. And now, if you take the center of this Weil chamber, this will also be invariant under the isometry group, provided that there are no extra elements which throw all these abelian subspaces around, so provided the space is not symmetric. So all of the isometry group will fix phi tilde unless M tilde is symmetric. And now it's not so difficult to prove that a group which, in non-positive curvature, a group, isometry group which fixes a point at infinity cannot satisfy the duality condition. So therefore, the isometry group violates duality condition. Again, unless M tilde is symmetric. And therefore, for example, one conclusion would be that the isometry group of such homogeneous spaces can never contain a uniform lattice. So in this case, K will be comparatively small, actually only under extra conditions on the structure of A and N, how they interact. Vicente-Cortez and Alexeyevsky have been able to compute the full isometry group. But what comes out is essentially it's small. And so now let's look at the general case. So assume in addition that M is an irreducible Hadamard manifold and G is some subgroup of the isometry group which acts co-compactly. First of all, we consider the connected component of the isometry group, G0. If that's trivial, we already have a discrete group, we are done. So we're in case 1 in this case. So what one has to do is use the standard Levi decomposition of such a connected Lie group. Here we have the maximal solvable normal subgroup, the radical. And here we have a semi-simple complement. And then we can look at the full group, and it may be written as the normalizer of L times G0. This is due to the fact that all semi-simple Levi factors are conjugate to each other. And we find a subgroup of finite index consisting of those elements which centralize L due to the fact that these two differ essentially, or the index is at most as big as the number of outer automorphisms of L, and there are only finitely many for a semi-simple group. And then one more step. So G, we may write L, the semi-simple group, we may decompose into its compact factors, its non-compact factors, and then we have the solvable radical. So start with one simple case. What happens if R is just trivial? So G0 is semi-simple. If it's semi-simple, then it contains the product of all non-compact simple subgroups L and C, and in this we may find a co-compact lattice, uniform lattice, and in this case, let's call it gamma. Now you see why I have chosen this complementary group, or actually it's not really complementary, there's an intersection, but as a lying in the centralizer of L, and now the centralizer of L times gamma is a discrete co-compact group acting on M tilde. So in this case, if the radical is trivial, we find a nice subgroup, just a discrete group, so it belongs to type 1. In L and C, yes. Mm-hmm. And we may have forgotten about, for example, this compact factor, but that does not do any harm. The group will still act co-compactly if we, for some reason, by some argument, get rid of compact subgroups. And now, second case would be we can't get rid of the solvable normal subgroup. So in this case, we would have to decompose further. In fact, we would choose the above mentioned Iwasawa decomposition of the non-compact semi-simple group. And then there's some work to be done to show that this K is actually compact. In general, it will contain the center, and if the center is and the quotient will be compact, and if the center is infinite, then K itself will not be compact. So, for example, like with the universal covering of SL2R, such problems occur. But here it's possible to show this K is compact, and then we may again get rid of to abbreviate that, of these two compact guys, and we will have this new group G still acting co-compactly, and its, or let's call it G tilde, and its connected component will be solvable. Okay, so now I should phrase the theorem. Suppose that irreducible Hadamard manifold is given such that some subgroup of the isometry group is closed and co-compact. And as I mentioned before, I will never worry about not knowing all of the isometry group. I'm always allowed to decrease, to make the group smaller, as I did here, as I did there, as long as it's still co-compact. Then G contains a co-compact closed subgroup G tilde, which satisfies one of the following. G tilde may be discrete, or it may be almost discrete. So now we're in case 3b, so now I'll assume that the connected component of G is solvable. So this case looks as follows. The group connected component will be solvable with flat orbits. So they will be, and actually these orbits are all parallel to each other and split off. So all of M tilde will turn out to be a Riemannian product of a Euclidean space and some additional space, and the connected component extransitively on each of these leaves E cross P. Whereas the projection to the isometry group of M tilde prime of the whole group G tilde is discrete. So that's still reasonably close to discrete, but it's always the case that Euclidean factors cause trouble and make results more complicated. But that's maybe something pretty close to discrete. Pardon? Right, yes. You're of course right, and actually that's appears to be stupid. But then I have to plug in irreducible here. That makes more sense. Thank you. Or third possibility, there exists a subgroup G tilde, which looks as in type B. It's a semi-direct product of a nilpotent normal subgroup and a semi-direct product of a nilpotent normal subgroup and a complementary group H. And here N is nilpotent, as I mentioned. And H is almost of type 2. That's why I needed these splitting groups with acting on a splitting space. Nilpotent, and H is an extension, a central extension of a group of type 2. In this sense, 1, 2, 3 of type 2 by a torus. So we start with discrete groups. We can't avoid having these extensions which with a solvable connected component acting transitively on Euclidean leaves, and then those might actually act by conjugation on some nilpotent group, and so in any case there there will be a group G tilde which looks like that. Maybe I should explain some particularly simple example where I could include several additional properties. For example, the H also acts co-compactly on some totally geodesic subspace, and this totally geodesic subspace would then split in a manner given by given in 2. So Euclidean times something else. And this can, of course, not occur if the curvature is negative. So in this case, everything becomes much simpler. G tilde might, of course, be a discrete group acting co-compactly. So you may call it a lattice, but you have to be aware that there might be torsion. Or secondly, G tilde is isomorphic to a semi-direct product just of a nilpotent group and a complementary subgroup Z. So in this case, we have a conjugation gives us a nice homomorphism from Z into the automorphisms, and this has an additional important property. It maps 1 to a contracting automorphism. So on the Lie algebra level, this would be a Lie algebra automorphism whose eigenvalues all have norm less than 1. Yes, so that looks much simpler, but that is what life is like. Maybe I'll try to explain just one aspect of the proof. We may essentially assume that or we will reduce to case 2, and in case 2, case 2 and 3. So by that I mean that the universal covering should be solvable of our group, the group we start with. The whole of G has a fixed point at infinity. let's call it Z. So some class of asymptotic geodesic rays. We choose some geodesic gamma, which belongs to this class of asymptotic rays, and investigate the parallel space of gamma. It's the union of all geodesics at constant distance from gamma. It's well known that these parallel spaces are always convex and closed. And in this case, due to co-compactness of the action, it's easy to see that they are also complete. So we can split off a Riemannian product. And now we have all these parallel geodesics, which make up the parallel space W. And also due to co-compactness, we find the following will be approached arbitrarily well. So let's call it gamma hat. So for all gamma hat, such that which belong to this asymptote class of asymptotes Z, there exists a unique geodesic gamma tilde such that the distance will tend to 0, not just Hausdorff distance of partial rays or so, but exactly including the right parametrization. I will only consider unit speed geodesics here. And this gives us a nice retraction. We may map, from any point we have a corresponding geodesic tending towards Z at infinity. We find a unique corresponding geodesic gamma tilde, and we may map gamma hat to gamma. So we find a retraction from M tilde to our parallel space, mapping some point on a geodesic gamma hat tending to Z to the corresponding point gamma tilde to Z. And this actually defines, which at first sight might look surprising, homomorphism from the whole group to the isometry group of W. We just restrict an arbitrary isometry phi to W, apply phi. Usually this takes us out of W, and then we apply the retraction again. And this is a group homomorphism with nice properties. And essentially, up to passing to suitable extensions and getting rid of some compact subgroups and so on. So essentially, this n will be the Nil radical of the kernel of this map. So essentially, n will be more or less the kernel of this homomorphism. This will be the normal subgroup, and H will be essentially up to a finite number of modifications, the stabilizer of W. So that appears, this group action on this parallel space appears to be very suitable and gives nice structure of the acting groups, and So in the beginning, these two groups won't. These two groups will intersect, but they will only intersect in a torus. That's why we need a central extension by a torus here. And but that's maybe all I can give as an indication of the proof right now. Thank you very much.